November 12, 1942, Richmond Shipyard No. 2, California, 0900 hours. A hull slides into San Francisco Bay, 4 days and 15.5 hours earlier. This ship did not exist. Now it displaces 14,245 tons, measures 441.5 feet long, and carries the name Robert E. Peary. Workers have assembled 250,000 prefabricated parts, completed nearly 50 miles of welding, and created a functional cargo vessel in less time than it takes most people to drive cross-country. The ship is ugly. President Franklin Roosevelt himself called these vessels ugly ducklings. The Robert E. Peary has a blunt bow, a boxy superstructure, and none of the grace that traditional maritime architecture demands. It looks exactly like what it is, an emergency construction built by people who had never built ships before, using techniques that violated every principle of traditional shipbuilding. It also represents something unprecedented in industrial history, not the speed record itself, which is largely a publicity stunt requiring massive preparation and coordination that cannot be sustained. The significance is what the record demonstrates. American industry has learned to build ocean-going cargo vessels the way Ford builds automobiles, in assembly lines, from interchangeable parts, by workers who learned their trades weeks ago. In June 1942, German U-boats sink 124 Allied merchant ships. That single month erases 830,000 tons of carrying capacity. Britain is starving. The Soviet Union is fighting desperately on the Eastern Front and needs American supplies. Operation Torch, the invasion of North Africa, requires moving hundreds of thousands of troops and millions of tons of equipment across the Atlantic. The Allies are losing the war of tonnage. The Robert E. Peary and the 2,709 other Liberty ships built between 1941 and 1945 will turn that equation around. Not because they are good ships. They are not, but because America can build them faster than Germany can sink them. This is not how anyone planned to fight the war. September 3, 1939. Britain declares war on Germany. Hours later, German submarine U-30 sinks the passenger liner Athenia west of Ireland. 112 passengers and crew die. The Battle of the Atlantic has begun. It will last 5 years and 8 months, making it the longest continuous military campaign of the war. Britain's survival depends entirely on maritime commerce. The island nation imports 70% of its food, all of its petroleum, most of its raw materials. Cutting those sea lanes means starvation, industrial collapse, and surrender. Germany knows this. Grand Admiral Karl Donitz, commander of the U-boat fleet, believes he can force Britain out of the war by sinking merchant ships faster than they can be replaced. The mathematics are straightforward. In 1939, Britain had 21 million tons of merchant shipping. Germany needs to sink approximately 750,000 tons per month to reduce that capacity faster than it can be rebuilt. Achieve that for 18 months and Britain cannot continue fighting. Initially, the numbers favor Germany. In 1940, U-boats sink 520 Allied ships. In 1941, 457. Traditional shipbuilding cannot match these losses. A merchant vessel constructed by conventional methods requires 6 to 8 months. Riveted hull construction is labor-intensive. Each ship is essentially custom-built, even when following standard designs. Skilled workers are scarce. Shipyard capacity is limited. The British Maritime Commission understands the problem but has no immediate solution. In 1940, facing desperate need, they order 60 emergency cargo ships from American yards. The design is basic. A simple tramp steamer based on plans from Joseph L. Thompson and Sons in Sunderland, England. The vessel is designated Ocean Class, 441 feet long, 57 feet wide, single cargo deck, 5 holds, powered by a 2,500 horsepower reciprocating steam engine of a design essentially unchanged since the 1880s. The British specify coal-fired boilers because Britain has coal but no significant oil production. They also specify riveted construction because that is what British shipyards know. The design is deliberately old-fashioned, slow, ugly, cheap. It uses proven technology that any competent yard can build without exotic materials or specialized skills. American shipyards begin construction in December 1940. The first vessel, Ocean Vanguard, launches August 16, 1941. By this time, the United States Maritime Commission has modified the design for American production. The changes are significant. First, oil-fired boilers replace coal. America has abundant petroleum and no desire to handle coal bunkers. Second, the superstructure is reconfigured into a single midships deck house instead of the British two-house design. This simplifies construction without affecting cargo capacity. Third, and most important, welding replaces riveting wherever possible. This decision will save the program and nearly destroy it. Welding offers enormous advantages. A riveted hull requires plates to overlap, consuming steel. Welding allows butt joints, saving weight. Riveting requires skilled workers who spend years learning the trade. Welding can be taught in weeks. Riveting is slow. 3 workers operate as a team. One heats the rivet. One places it. One drives it home with a pneumatic hammer. Welding is fast. A single operator with an electrode can lay down bead after bead of fused metal. The Maritime Commission embraces welding enthusiastically. The emergency cargo design, now designated EC2 for Emergency Cargo Type 2, will be predominantly welded. Some frames remain riveted to the shell, but most of the hull consists of steel plates welded together in continuous seams. This creates, effectively, a single piece of metal 441 feet long. Nobody fully understands the implications. The first American-built emergency cargo ship, SS Patrick Henry, launches December 30th, 1941, 3 weeks after Pearl Harbor. The United States is now at war. The Maritime Commission's emergency program becomes critical to national survival. The initial order of 60 ships expands to 260, then 500, then more than 2,000. The program needs a better name. Admiral Emory Land, chairman of the Maritime Commission, reviews the design with President Roosevelt. The president studies the blueprints and offers his assessment. "I think this ship will do us very well," he says. "She will carry a good load. She is not much to look at, though, is she? A real ugly duckling." The name sticks unofficially, but the Maritime Commission wants something more inspiring. In May 1941, they settle on Liberty Fleet. The first ship was named Patrick Henry after the revolutionary who demanded liberty or death. Newspapers begin calling them Liberty ships. The designation becomes permanent. Building them will require reinventing shipbuilding. Henry John Kaiser is not a shipbuilder. Born in 1882 in upstate New York, he spent his youth in various trades before moving west in 1906. He established a road construction business in the Pacific Northwest and discovered a talent for logistics and large-scale project management. His companies built highways, dams, bridges, the Hoover Dam, the Grand Coulee Dam, the San Francisco-Oakland Bay Bridge. Kaiser's approach to construction emphasizes speed and efficiency over traditional methods. He thinks in terms of systems, supply chains, mass production. When the Maritime Commission needs yards to build emergency cargo ships, Kaiser's consortium wins contracts despite having never built a ship. He begins constructing shipyards in Richmond, California, Portland, Oregon, and Vancouver, Washington specifically, to build Liberty ships using techniques no traditional shipyard would attempt. Traditional shipbuilding works from the keel up. Workers assemble the ship on the ways one frame at a time. Each frame is positioned, secured, plated. The process is sequential. One trade waits for another to finish. Bottlenecks are inevitable. Kaiser rejects this entirely. He designs his yards for horizontal construction. The ship will be assembled from prefabricated modules built simultaneously in different areas of the yard. Bow sections, stern sections, deck houses, bulkheads all fabricated separately, then lifted by cranes and welded into position on the ways. The hull becomes an assembly of large components rather than an accumulation of small pieces. This requires rethinking every aspect of construction. Components must be built to precise tolerances so they fit together. Transportation paths must be planned to move multi-ton modules without interfering with other work. Cranes must be positioned to reach every part of the assembly area. Most critically, welders must be trained by the thousands. Kaiser establishes welding schools at his yards. Classes run 24 hours. Students with no industrial experience learn to strike an arc, maintain proper electrode angle, control heat input, produce sound welds. Training lasts 3 weeks. Then they go on to the ships. This creates predictable problems. Inexperienced welders produce flawed welds, incomplete penetration, slag inclusions, porosity, undercut. Each flaw becomes a potential crack initiation site. Quality control struggles to inspect the enormous volume of welding, 50 miles of weld on each ship. Inspectors cannot examine every inch. Defects slip through. But the system works because it generates volume. Kaiser's Richmond yards alone employ 90,000 workers at peak production. The Oregon yards another 30,000. 3 shifts per day, 7 days per week. Multiple ships under construction simultaneously on parallel ways. The organization operates like a factory, not a traditional shipyard. By mid-1942, Kaiser's yards are launching Liberty ships in 30 days, then 20 days. The competition between yards becomes intense. Kaiser's son Edgar manages the Oregon operation. Clay Bedford runs Richmond. They compete to set construction records. Oregon launches a ship in 23 days. Richmond responds with 21. Oregon counters with 13. Richmond finishes one in 7 days. The Maritime Commission eventually stops these stunt ship demonstrations because they disrupt normal production. The extreme coordination required to achieve record times consumes resources better spent building ships at sustainable rates. But the stunts prove the concept. Shipbuilding can be industrialized. The average construction time settles at 42 days by 1944. Some yards are faster, others slower. But the aggregate production is extraordinary. In 1941, 7 Liberty ships are delivered. In 1942, 597. In 1943, 1,235. In 1944, 1,050. Production peaks at 3 ships per day. The specifications remain consistent across all vessels. Length 441.5 feet. Beam 56 feet 10 3/4 inches. Draft 27 feet 9 1/4 inches. Gross tonnage 7,176. Displacement tonnage 14,245. 5 cargo holds with combined capacity exceeding 459,000 cubic feet. 3 holds forward of the engine room. 2 aft. Cargo capacity 10,800 deadweight tons. Alternatively, 2,840 jeeps, or 440 tanks, or 230 million rounds of rifle ammunition, or 300 airplanes on deck. The ships carry 5-ton booms for each hold. One 50-ton boom at hold number 2, and one 30-ton boom at hold number 4. Propulsion. Single screw, driven by one triple expansion reciprocating steam engine producing 2,500 shaft horsepower. Fed by 2 oil-burning boilers operating at 220 pounds per square inch. Maximum speed 11 knots. Cruising speed 10.5 knots. Range 17,000 nautical miles at 11 knots. The crew consists of 41 merchant mariners, plus 12 to 25 naval armed guard personnel. Armament varies, but typically includes one 4-inch gun mounted aft for anti-submarine defense, one 3-inch gun forward, 8 20mm anti-aircraft cannons, and various machine guns. Early ships carry minimal defensive weapons. Later ships are more heavily armed as threat levels increase. The design makes no pretense of sophistication. These are minimum viable ships built to a 5-year design life. The assumption is that most will be sunk before wearing out. Those that survive will be scrapped after the war. Nobody expects Liberty ships to operate beyond 1950. They are built to be expendable. January 1942. U-boats begin Operation Paukenschlag, drumbeat, attacking shipping off the American East Coast. Admiral Donat sends 5 Type 9 long-range submarines to American waters. The results exceed expectations. In the first wave, U-boats sink 25 ships totaling 200,000 tons. The Americans have no coastal convoy system. Ships sail independently, silhouetted at night against shore lights that remain lit despite the war. Defenses are non-existent. The slaughter intensifies. By April 1942, U-boats have sunk nearly 500,000 tons off the East Coast alone. In May, the killing extends to the Caribbean and Gulf of Mexico. 375,000 tons sink in those waters over 3 months. U-boat commanders call it the second happy time. Targets are plentiful. Defenses are weak. Loss rates for U-boats are minimal. June 1942 becomes the worst month of the war. 124 Allied ships sink. 830,000 tons lost. The U-boats are winning. But the equation is shifting. American shipyards delivered 7 Liberty ships in 1941, most completing late in the year. In January 1942, 17 more deliver. February, 26. March, 37. The numbers accelerate month by month as more yards come online and learning curves flatten. By June, 65 Liberty ships deliver. By December, 97 per month. Each ship carries 10,000 tons. 97 ships equal 970,000 tons of new carrying capacity per month. In December 1942, U-boats sink 117 Allied ships totaling 660,000 tons. For the first time, new construction exceeds losses. The crossover point has arrived. America is building ships faster than Germany can sink them. Dönitz recognizes the problem. He needs more U-boats. Submarine construction receives absolute priority in German war production. 300 U-boats are operational by the end of 1942. But Allied countermeasures are improving. Convoy systems extend to American waters. Escort vessel numbers increase. Radar-equipped patrol aircraft make surface operations hazardous. Long-range aircraft close the mid-Atlantic air gap where U-boats previously hunted with impunity. May 1943 marks the turning point. U-boats sink 50 Allied ships. Allied forces sink 41 U-boats. The exchange rate is reversed catastrophically. Dönitz withdraws U-boats from the North Atlantic. The battle is effectively over, though U-boats continue operations at reduced intensity through war's end. The Liberty ships have done their job, not by being good ships, by being numerous. But they have another problem. January 16, 1943. Portland, Oregon. SS Schenectady sits at the fitting-out dock, the T2 class tanker. Closely related to the Liberty ship design and built using identical methods, completed sea trials days earlier. The ship is unloaded. The weather is cold, temperatures hovering near freezing. Water temperature 39 degrees Fahrenheit. At approximately 0300 hours, without warning and with a report audible for over a mile, the deck and sides fracture just aft of the bridge superstructure. The crack extends through the deck, down both sides of the hull. Through longitudinal bulkheads and bottom girders, the ship splits completely in two, hinged only at the keel bottom. The fracture propagates in seconds. Nobody aboard is injured because the ship is stationary in calm water. Photographs of SS Schenectady show a ship cleanly broken in half. The deck edges are sharp, showing classic brittle fracture. No tearing. No ductile deformation, just sudden separation, as if the ship were made of glass. This is not an isolated incident. By mid-1943, reports accumulate of Liberty ships developing cracks, deck cracks, hull cracks, some during construction, some during loading, some at sea in heavy weather, some sitting quietly at anchor. Nearly 1,500 instances of significant brittle fractures are documented during the war. 12 ships break completely in half. 3 are Liberty ships. The rest are T2 tankers. SS John P. Gaines breaks up November 24, 1943 off Alaska while en route from Dutch Harbor to Seattle. Air temperature near freezing. Heavy swells. The ship fractures and splits in two. The bow presumably sinks. The stern drifts ashore. 10 crew members die. Investigations initially focus on welding quality. Inexperienced workers. Poor technique. Inadequate inspection. The logic seems obvious. Traditional riveted ships do not break in half. These new welded ships do, therefore welding must be the problem. This conclusion is wrong. Constance Tipper, an engineering researcher at Cambridge University, investigates fractures in a British-built sister ship, Empire Duke. Loaned for testing, her analysis reveals the actual failure mechanism. The steel itself is the problem, not the welds. The steel used in Liberty ship hulls suffers from a property called ductile brittle transition. At normal temperatures, the steel is ductile. It can deform, absorb energy, resist crack propagation. Below a critical transition temperature, the same steel becomes brittle. It cannot deform. Cracks propagate explosively with minimal energy input. The critical temperature for Liberty ship steel averages around 40 degrees Celsius. That is 104 degrees Fahrenheit. Ships operating in the North Atlantic routinely experience temperatures below this critical point. The hull steel transitions to brittle behavior. A small crack, perhaps at a stress concentration like a square hatch corner or a weld defect, begins to propagate in a ductile material. The crack would arrest in brittle material at low temperature. The crack runs. The all-welded construction makes everything worse. Riveted hulls consist of discrete plates connected by rivets. A crack reaching the edge of one plate stops because the adjacent plate is separate. The crack cannot jump across the rivet line. Welded hulls are continuous. A crack propagating through one plate continues into the next and the next. Nothing stops it except reaching the end of the ship. 52% of serious Liberty ship fractures originate at hatch corners. The hatches have square corners, classic stress concentrators. Naval architects have known for decades that corners concentrate stress and should be rounded. Liberty ship hatches are square because the design is simplified for rapid production. The corners meet welded seams. The combination creates perfect crack initiation sites. Additional factors contribute. Liberty ships are frequently overloaded. The nominal capacity is 10,000 tons, but wartime necessity often requires carrying 12 or 14,000. The extra weight increases stress throughout the hull. Heavy weather adds dynamic loads. Ships hogging and sagging in waves experience enormous bending moments. Cold temperatures make the steel brittle. A small crack forms at a hatch corner. Stress concentrates. The crack propagates. The weld offers no resistance. The crack runs through the hull in seconds. The engineering community develops solutions quickly. Hatch corners are reinforced with curved crack arresters. Riveted straps are installed at critical locations to prevent crack propagation. Steel specifications are modified to require better low-temperature toughness. Welding procedures are improved to reduce defects. Ships are routed through warmer waters when possible. These fixes work. The catastrophic failure rate drops dramatically. Later, Liberty ships rarely experience serious fractures, but approximately 1,200 Liberty ships suffer significant cracks during the war. About 30% of the total built. Most are repairable. Some require extensive rebuilding. A few are assembled from the bow of one ship and the stern of another. Possible only because the standardized design makes all hulls interchangeable. The Liberty ship structural problems become a milestone in engineering history. The failures demonstrate that material selection matters as much as structural design. They prove that welding changes structural behavior in ways traditional analysis cannot predict. They establish the field of fracture mechanics as a distinct engineering discipline. Constance Tipper's work on ductile brittle transition becomes foundational to understanding material failure. But during the war, the structural problems are secondary. Liberty ships are breaking, but they are also delivering cargo. The calculus is brutal but clear. Even accounting for structural failures and U-boat sinkings, the ships are arriving faster than they are being lost. That is sufficient. 2,710 Liberty ships complete between 1941 and 1945. 18 shipyards across the United States build them. Kaiser's 7 yards build 821 Liberty ships, 30% of the total. His yards also build 219 Victory ships. An improved design introduced in 1943 with turbine propulsion and higher speed. The Liberty ship construction program represents the largest production of a single ship type in history. The closest historical parallel is the Hog Islander standardized cargo ship program from World War I, which produced 122 ships. Liberty ship production exceeds that by factor of 22. The ships are named after prominent deceased Americans. Patrick Henry, the first, after the Revolutionary, signers of the Declaration of Independence. Historical figures. The last 100 are named for merchant seamen who died in the war. Any organization raising $2 million through war bonds can suggest a name. The actual cost per ship varies between $1,543,000 and $2,099,000 depending on yard and accounting method. The ships serve everywhere. North Atlantic convoys carrying supplies to Britain. Murmansk Run supplying the Soviet Union through Arctic waters. Pacific operations supporting island campaigns. North African invasion. Sicily. Italy. D-Day. The ships carry everything. Food. Ammunition. Vehicles. Aircraft. Fuel. Troops. They operate under American, British, Soviet, and other flags through Lend-Lease. 200 Liberty ships are lost to enemy action during the war. Torpedoes. Mines. Air attack. Kamikaze strikes. Surface action. The loss rate is approximately 7%, far lower than the 50% loss rate initially feared. The combination of improving convoy tactics, increasing escort strength, and Allied air superiority protects the ships reasonably well. More Liberty ships are damaged than sunk. Several hundred suffer casualties from near misses, fragmentation damage, or equipment failure. Most are repaired and returned to service. The standardized design makes parts and repairs straightforward. Damaged ships can even be cannibalized to repair others. After the war, many Liberty ships enter commercial service. 835 join the American merchant fleet. Hundreds more operate under Greek, Italian, and other flags. The expected 5-year design life proves conservative. Ships operate for decades with proper maintenance. Some serve into the 1970s. The last Liberty ship scrapped is demolished in 2003, 58 years after the program ended. Several Liberty ships are lost to mines after the war. German and Japanese minefields are inadequately cleared. Ships strike mines in supposedly safe waters. Pierre Gibault is scrapped after mine damage off Greece in June 1945. Colin P. Kelly Jr. takes mortal damage from a mine off Belgium the same month. William J. Palmer hits a mine near Trieste in August 1945 while carrying horses from New York. The ship rolls over and sinks in 15 minutes. Crew and most horses are saved. Robert Dale Owen, renamed Calliope under Greek flag, breaks in 3 and sinks in the northern Adriatic after mine strike in December 1947. 2 Liberty ships survive today as operational museum vessels. SS Jeremiah O'Brien in San Francisco and SS John W. Brown in Baltimore. Both ships sail regularly under their own power, maintained by volunteer crews. Jeremiah O'Brien crossed to England in 1994 for the 50th anniversary of D-Day, demonstrating that a properly maintained Liberty ship can still make ocean crossings. The ships represent more than a production achievement. They demonstrate that industrial methods can be applied to complex engineering challenges, that speed and quantity can compensate for individual quality, that traditional practices can be abandoned when circumstances demand. They also reveal the limits of that approach. Building faster than you understand creates problems. The structural failures result from adopting welding without comprehending how welding changes structural behavior. The inexperienced workforce produces flawed work that adequate inspection would catch, but rapid production cannot accommodate. The drive for speed overrides engineering judgment about stress concentrations and material properties. These problems are recognized and solved, but only after multiple catastrophic failures and hundreds of less serious ones. The learning process costs ships and lives. In a war where the alternative is losing, the cost is acceptable. In peacetime construction, it would be inexcusable. The Liberty ship program's true significance emerges in its industrial impact. Kaiser's mass production techniques influence post-war shipbuilding worldwide. Japanese and South Korean shipyards adopt similar approaches in the 1950s and 60s, creating the dominant shipbuilding industries of the late 20th century. Modern shipyards still use modular construction, prefabrication, and extensive welding. The methods Kaiser developed building Liberty ships became standard practice. The program also demonstrates American industrial capacity. Between 1941 and 1945, American shipyards produce 5,500 ocean-going vessels. Liberty ships comprise half of that total. Combined wartime merchant shipping construction exceeds 15 million tons. This is accomplished while simultaneously producing warships, aircraft, vehicles, weapons, and ammunition in unprecedented quantities. No other nation matches this output. Britain builds ships but cannot match American volume. Germany tries to replace U-boat losses and fails. Japan's shipbuilding focuses on warships and cannot replace merchant losses. The Soviet Union receives Liberty ships through Lend-Lease but builds few of its own. American industrial capacity simply overwhelms all competitors. This capacity rests on specific advantages: natural resources, particularly steel, a workforce of 140 million people, geographic isolation from combat, but also organizational innovation, the willingness to abandon traditional methods, the ability to scale production rapidly, the application of mass production thinking to complex products. Henry Kaiser becomes a national hero. Time magazine features him repeatedly. Newspapers celebrate him as a miracle worker. President Roosevelt considers him as a potential vice presidential running mate in 1944. A public poll near war's end names Kaiser the American civilian who contributed most to victory. A 1946 poll lists him as a presidential prospect. His success comes from seeing shipbuilding as a production problem rather than a craft tradition. Traditional shipbuilders know ships, but think in terms of individual vessels. Kaiser knows production and thinks in terms of systems. He asks what prevents faster building and eliminates those constraints. Skilled labor shortage. Solution: simplify the work so unskilled labor can do it. Sequential construction bottlenecks. Solution: build components in parallel and assemble them. Material shortages. Solution: design ships using available materials with minimal special requirements. This systematic approach, applied ruthlessly, produces results that traditional shipbuilding cannot achieve, but it also produces a different kind of ship. Liberty ships are crude compared to peacetime construction. They are noisy, uncomfortable, slow, inefficient. Crews dislike them. Maritime professionals consider them barely adequate. But they float, they carry cargo, and they arrive in sufficient numbers to win the war of tonnage. That is all they need to do. The British survive because enough Liberty ships arrive fast enough. The Soviet Union fights on because American supplies reach Murmansk and Vladivostok aboard Liberty ships. The D-Day invasion succeeds because Liberty ships deliver overwhelming material superiority to British ports. The Pacific campaigns succeed because Liberty ships maintain supply lines across thousands of miles of ocean. The ships themselves are unremarkable. Their aggregate effect is decisive. This is industrial warfare in its purest form, not individual quality or tactical brilliance. Mass. Volume. The relentless accumulation of material superiority until the enemy cannot match it. Liberty ships embody this approach. They win not by being better, but by being more numerous than the enemy can counter. Admiral Donitz understood this. In his post-war memoirs, he identifies the Liberty ship program as the factor that defeated the U-boat campaign. German submarine production peaked at 30 U-boats per month in 1944. American shipbuilding peaked at 90 Liberty ships per month in 1943. Each U-boat might sink 10 ships before being sunk itself. But if America builds 90 ships per month and Germany sinks 30, the arithmetic favors America. Donitz could not win a war of attrition against American industrial capacity. Nobody could. The Liberty ship program made that clear to anyone watching. America was not just producing enough to replace losses. It was producing enough to build up reserves, expand operations, and overwhelm enemy capabilities through sheer volume. The ugly ducklings turned out to be exactly what the situation required. Not elegant, not sophisticated, not even particularly well built, but adequate and numerous, and arriving faster than the enemy could sink them. In 4 days and 15.5 hours, the workers at Richmond Shipyard No. 2 proved that a nation's industrial capacity could be weaponized as effectively as its army. The Robert E. Peary's record stood not because it was the best Liberty ship. It stood because it demonstrated the principle. Shipbuilding could be industrialized. War could be won not by building better ships, but by building more ships. Hitler could not sink them fast enough. Nobody could. The production line defeated the submarine. The assembly line defeated the torpedo. The welding torch, for all its flaws, defeated the war of attrition. The Liberty ships sailed on, carrying the war to its conclusion, one ugly duckling at a time.